Okay, welcome back. Now, I've given you a crash course on logarithms. We can go over this again, but you'll see some of these things while we do the actual process. So I want to show you, I'm going to show you how logarithms become useful in this calculation or in this subject. So, as we've established, I uncovered something, I didn't mean to do that. So this, let's just take this right over here. If you look at what I've written here, I've shown you a trick with logarithms that you will get in grade 11 math, but I'm showing you it early because it helps you with radioactive half-life. This trick, if you look at this, what I have here is log 10, base 10, of 10 to the power of 3 is the same thing as saying 3 times the log base 10 of 10. So what I've done here is I've actually taken this exponent and I've brought it out in front. Now you can try this. Punch these numbers into your calculator. Punch in 10 to the power of 3 and take the logarithm of that. So press the logarithm button. You should get 3. Now, take the logarithm of 10 and multiply it by 3. You're going to get the same answer. Try it with a couple of different numbers right now. Pause the video. Try this with a couple of different numbers to convince yourself that it works. Okay, and the math deriving it, the math behind it, I'm not going to get into. It's not something you need for now, but it's good to convince yourself that it works because then you're more likely to remember it and use it. Okay, so the big question I've put here, of course, is why do I need to know this? So I'm going to show you how this makes your radioactive half-life calculations much, much easier. But we'll get there in a minute. First, I'm going to point out, when we did our question, this is the same question we did at the beginning of the first lesson, or the middle of the first lesson, I guess I should say. What we did, I told you these two values, the initial mass, the final mass, 225. And what I did was I put them in a fraction, 25 over 200. If you reduce this fraction, divide both numbers by 25, you get 1 over 8. 8 is 2 to the power of 3, so it's the same thing as saying 1 over 2 to the power of 3. And if you look at this, that's the same thing as 1 to the power of 3 over 2 to the power of 3, which means we can write this right here. It's 1/2 to the power of 3. That tells us 1/2 times a half times a half. What it's saying is the ratio of the final mass to the initial mass is the same as 1/2 to the power of the number of half-lives that have elapsed. So in this case, 25 over 200, it was 3 half-lives. So it was 1/2 to the power of the number of half-lives that have passed. So this equation, taken a little more generally, and read through this in the one in the textbook, is this one here. So I just said this, the final mass divided by the initial mass is the same as 1/2 to the power of however many half-lives have occurred. Now, to know the number of half-lives that have occurred, really there are two numbers that make that up. The actual elapsed time, above that was 30 hours, and the half-life, which we worked out to be 10. So 30 over 10 equaled 3, and that took us back to what we had up here. Make the screen big again. Okay, so this here, I'm going to erase what I just wrote in. This stuff here, this big equation here, this is the generic half-life equation. I believe that's in the textbook and you can follow it. So basically in this case, in the question I just asked you, you were supposed to solve for half-life, and I gave you this, this, and this, and the half is already there because that's half-life. All right. Now, that one is fairly easy to solve based on being able to just multiply by a half. And it just worked out that the final mass divided by the initial mass was exactly a power of 1/2. But it's not always going to be that case. So I have the question at the bottom. If I gave you the time, the half-life, and the initial mass, you could probably work out mathematically the way we've done exactly what the final mass is going to be. However, we can do it a little more easily. Where are we? Here we go. So here's our half-life equation. This is the same thing I just wrote, but what I've done here is I've multiplied both sides by the initial mass to get the initial mass on the right side of the equation. Either form is useful, all right? And you're going to work out a couple of more forms, one solving for each one of the variables in the equation. So here's the question. If we plug the numbers into this question, if you remember, we're looking for the half-life. We're going to have 25 equals 200 times 1/2 to the power of 30 over the half-life. Okay? So 30 hours over however many hours is one half-life. When we want to solve this, we're going to have to do something kind of tricky with this equation. Let me just take a quick look ahead. Yeah. Okay, so here's where that trick comes in handy. First thing I'm going to do is I'm going to get my, I'm isolating for that half-life value there. That's what I'm looking for. So I'm going to go 25 over 200 equals 1/2 to the power of 30 over HL, the value I'm solving for. Here's where the trick comes in. I'm going to take the logarithm of both sides. Remember, algebraically, whatever you do to one side, you do to the other. But if you can do it to both sides, it's legitimate. So I'm going to take the logarithm of both.
Mr. Breakwell, would you come to the South Main office, please? Mr. Breakwell? Mr. Breakwell, come to the South Main office, please.
Okay, so here's what I've done. 25 over 200 is equal to 1 over 8. I took the logarithm of both sides. And now you remember the trick, and if you don't, go back in the video. But if you remember, this is the exponential term, and it can be brought down in front. So what that's going to give us is log of 1/8 over 8. Oops. Log of 1 over 8 equals 30 over 1 half-life times the logarithm of 1/2. And now what we've managed to do, the trick that we've managed to pull off here is we've taken this half-life term out of the exponent. It's no longer in the exponent, so now we can solve for it. All right, if we multiply both sides by half-life, we get half-life times log of 1/8 equals 30 log of 1/2. And we know all those values. To solve for the half-life, or isolate for the half-life, we're going to do this. 30 log 1/2 all over log of 1/8. And now these are all values you know. So you can solve for the half-life. Now plug those numbers in, you should get the same answer that we got before. Quick thing to point out on these things. Make sure that these two numbers, the 25 and 200, are in the same unit. Make sure that these two numbers are in the same unit. If they're not, your answer is going to be wrong. If you do 30 hours and try to do a half-life in days, they're not going to match. It's not going to work out. These should end up unitless. All right? The second thing is, sometimes you're given an activity, which is a radioactive activity. It's a number of decays per second. And you can treat that exactly like math. So whatever you're given in terms of activity, you can just put that value right in here. Okay, so you'll have an initial activity, a final activity. Activity is proportional to the mass of the substance. All right, next thing, some examples. You'll notice that in each of these cases, I'm asking for a different one of the values, a different one of the variables. So you're solving for each of the 4 variables. What I recommend is right now, before you try these questions, solve that equation for the 4 different variables. Then plug these numbers in to get the answers. And I'll give you a hint. The textbook is a wonderful resource to use. I'll take these numbers up in the morning. Good luck.